We're going to start the study of solid-state chemistry with a look at the crystal structures of extended solids. And to understand those, we need to understand something called translational symmetry. So you can look at the structure of a solid, and we can broadly classify all solids into one of two types. On the one hand, we can have a crystalline solid, as shown here on the left for iron pyrite, fool's gold. And in a crystalline solid, within the solid we have a regularly repeating pattern of atoms that are repeated over and over again. Kind of like you can build up a wall from many, many identical bricks. You can build up a crystal from many, many regularly repeating units. The other kinds of solids are called amorphous solids. And in those solids, we don't have this long-range repeating pattern of atoms. Okay, so obsidian, shown here, sometimes called volcanic glass, is a good example of an amorphous solid. The glass that you find in the windows, in the beakers in lab, etc., that's another example of an amorphous solid. And in these cases, it might be better to think of the arrangement of atoms as something of a frozen liquid. So let's consider crystalline solids in a little bit more detail. How can we define or characterize this repeating unit of atoms? And that takes us to really the subject of this lecture, which is translational symmetry. So in a crystal, we have a lattice of points, and each point in the lattice, the surroundings of that point are identical. Now here, I'm going to talk about lattices and crystal structures in 2 dimensions because it's just easier to visualize. But the ideas that we talk about in 2 dimensions can be extended completely analogously to 3 dimensions, and we'll do that toward the end of the lecture. Let's take a look at a generic 2-dimensional lattice. In a 2D lattice, we have an infinite array of lattice points, and the surroundings of each lattice point need to be identical. So if you were an observer to stand on one lattice point, everything as far as the eye could see would be the same on any lattice point. Mathematically, we can generate a lattice through the operation of 2 vectors, which are called the lattice vectors, here A and B. So if we were to call this point the origin, and then extending out from the origin, we can define the position of any point in the lattice by just a linear combination of those 2 vectors. For example, this lattice point we can get by 2 of lattice vector A and 3 of lattice vector B. And we could do that for any point in the lattice. Now, the 2 lattice vectors here, A and B, define a parallelogram, which I've shown in gray here. And that parallelogram, that is our repeating unit. This is the brick from which we're making the wall. And we could tile all of the space here by basically sliding together these different parallelograms. Okay, so the unit cell is the repeating brick. Now, how many different kinds of lattices are there in 2 dimensions? And to answer that question, what I'd like you to think about is how many different shapes can we use to tile 2-dimensional space? Spoiler alert, it's not a very big list. Here I show 8 different shapes. We have the arbitrary parallelogram, shown over here, and then we've got a few other more specific parallelograms, like the square and the rectangle and the rhombus. And then we've got some shapes which are not parallelograms, but which some of these can also be used to tile space. We're going to pause the video right now, and I want you to look at all of these shapes and figure out which ones tile space and which ones do not. And by the way, feel free to come up with other shapes that I might not have included here if you think that they can tile space. Okay, well, what did you come up with? Well, one of the shapes that does not tile space is the pentagon. So if we were to take pentagons and just put them together here like this, you can see that they don't tile space. The most straightforward way to do it is not to allow you to rotate the shapes. But with a pentagon, even if I said you can rotate that shape freely, can you then tile space? Now the answer is still no. No matter how you try to pack together a bunch of pentagons, you can't tile two-dimensional space. And that leads us to a conclusion. That's true in two-dimensional crystals that we'll see also in three-dimensional crystals. Shapes that have two-fold, three-fold, four-fold, and six-fold rotation axes are consistent with two-dimensional or three-dimensional translational symmetry of a lattice. But a shape or a molecule that has a five-fold axis, a 10-fold axis, an 8-fold axis, those shapes are not consistent with long-range packing into a crystal. And so we don't find those kinds of symmetry elements in crystals. Now, returning to the list, what I find when I do the analysis is that I cannot tile space with pentagons. I cannot tile space with octagons. I can easily tile space with the parallelogram, with the square, with the rectangle, with the rhombus, and with the hexagon. The triangle is a little bit iffy. I cannot tile space with an equilateral triangle by just stacking them next to each other. The only way I can do that is if I start rotating the triangles. But when I rotate all the triangles, I find I can tile two-dimensional space. As we'll see, that does not lead to a truly unique lattice. Let's come back to the triangle later. But if we look at the others, we see that we have 5 shapes that can tile space without rotating them, just by translating them. And it turns out that there are 5 lattices in 2 dimensions. Now, we did say that the unit cell has to be a parallelogram. And for 4 of these 5 shapes, the shape itself is a parallelogram. And so that can be the unit cell. But the hexagon is certainly not a parallelogram. So if we tile space with hexagons and we build a lattice up from that packing, what kind of a unit cell do we get? I'm going to pause for a second and have you think about that, and then we'll come back and discuss it. Okay, to answer this question, let's start with a hexagon, and now let's tile a bunch of hexagons together. In theory, infinitely, but here we're just going to do this many hexagons. Now let's put a lattice point at the center of each hexagon. Okay, now let's look for what is our unit cell. In other words, what are the lattice vectors that would generate this set of lattice points? That's what we really want to know. And once we find the lattice vectors, of course, they will define a parallelogram that's going to be our unit cell. And so that unit cell would look like this. So here we see shaded in cyan a unit cell that if we were to repeat that everywhere, you'd see the corners of that parallelogram would all lie on these lattice points. Okay, so this is our unit cell, and that means this vector A and this vector B are the unit cell vectors. You might say, well, that's just a rhombus. Yes, it is a rhombus. A and B are equal, but it's a special kind of rhombus because the interior angles are not arbitrary. This angle must be 60 degrees, and this angle must be 120 degrees. That's a necessary consequence of the 6-fold symmetry of the hexagon. And so now we're ready to say what are the unit cells and their shapes and the relationships between the unit cell vectors for these 2-dimensional crystal systems. So here we see the square lattice, where the unit cell is a square. A and B are equal, and the angle between them is 90 degrees. They're at right angles to each other. We see the rectangular lattice, which is similar, 2 vectors that are perpendicular to each other, but the vectors themselves now are no longer necessarily of the same length. We can see this oblique lattice, it's called, which is got a unit cell that's an arbitrary parallelogram. So A and B are not necessarily equal, and gamma can be anything. It's not limited to a specific value. And then we have the hexagonal lattice that we just talked about. And here, A and B are equal to each other, and angle between them, as shown here, is going to be precisely 120 degrees. Now, we haven't yet talked about point symmetry elements like rotation axes and mirror planes. But most of you will be familiar with that. And it turns out that it's not just the shape of the unit cell that's important. There's also a kind of point symmetry operation that's associated with each of these crystal systems. So for a square lattice, we have a fourfold rotation axis. And if you have two-dimensional crystal and you see it has a fourfold rotation axis, well, the unit cell must be a square because we don't find fourfold rotation axes in any of the other lattices. If you have the hexagon, now of course the hexagon itself has a sixfold rotation axis, and a sixfold rotation axis can be a defining symmetry element of a hexagonal lattice, but we can also have hexagonal lattices that have threefold rotation axes. So either a sixfold or a threefold rotation axis, the presence of that tells us we have a hexagonal crystal. If you have a rectangular unit cell, you might have a twofold rotation axis, although that's not required, but you will have either a mirror plane or something called a glide plane that we haven't yet discussed. And if you have the oblique lattice, then you don't have to have any symmetry other than just the translational symmetry of the repeating unit. So there might not be any rotational symmetry. There might not be any kind of mirrors. In fact, there cannot be mirrors, and there cannot be rotation axes. The only symmetry we can have in an oblique lattice would be an inversion center. Now, if we look at these, you would say, oh, there's only 4 of these. But when we were tiling shapes, we had 5 shapes that we could tile 2D space with. So what about the rhombus? Well, the rhombus I'm showing here. Okay, so if you have the rhombus, yes, you can get a two-dimensional lattice. The thing that's a little bit different about the rhombus is that whenever you have a rhombus, I could draw a unit cell that is a rectangle with lattice points at the corners and another equivalent lattice point at the center of the rectangle. Okay? Maybe you should look at this for a minute to convince yourself that anywhere I draw a rectangle, I'm going to have a lattice point at the exact center of that rectangle. This lattice is actually called a centered rectangular lattice. And we have a choice of how we want to define the unit cell. We can use what's called the primitive unit cell, which is a rhombus, or we could use this larger rectangular unit cell that has a lattice point at the center. And this is called the centered unit cell. The area of the centered unit cell, because it contains 2 lattice points, is going to be twice that of the primitive unit cell. Later on, we're going to talk about putting atoms inside the unit cell, and we'll see that not all of the atoms are on the lattice points. And so the thing about this kind of centered lattices means wherever we have an atom, there has to be an identical atom that's located 1/2 of the unit cell vector A plus 1/2 of the unit cell vector B from the original atom. Now you might say, could I not have examples of centered lattices for square or hexagonal or oblique? And the short answer is no. And the reason why I'm going to illustrate with the hypothetical centered square lattice. So let's take a unit cell that's a square. Let's put a lattice point at the center. And now let's build up a 2-dimensional array of points. So why wouldn't I use this centered square unit cell? Well, to answer that question, let's take a look at the primitive unit cell. The primitive unit cell is shown here. And you can see that it is, in fact, half the area of the centered unit cell. But the thing that's different than the last slide is that this primitive unit cell is also a square. So I have a choice of this square for a unit cell or this square as a unit cell. And if I can draw the same shape, the same symmetry, I always am going to pick the smallest possible unit cell. And so we would always choose this primitive square over the centered square. So this lattice is not a centered square lattice. It is a primitive square lattice. Now, what I would like you to do is to look at these 2 patterns of circles. You can think of them as atoms if you like. And I want you to find the unit cell in each case, and then by finding the unit cell, you will determine the kind of lattice. Is this one of the 4 primitive lattices? Square, rectangular, hexagonal, oblique, or is it perhaps a centered rectangular lattice? It's one of those 5. Then while you're at it, since you've got the unit cell, you can figure out the empirical formula by adding up the contents of what's inside the unit cell. So let's pause the video, put you into groups, and I want you to solve this problem, and then we're going to talk about it. Okay, welcome back. Let's go through the answers now. In the upper half of this slide, the unit cell looks something like this. It's a square with the white atoms at the corner of the square, and then the dark atom or the dark circle at the center of the square. So we see this is a square Bravais lattice. And furthermore, how many atoms are there? Well, you can see that there's parts of 4 white atoms in the unit cell, but each of those, only 1/4 of the circle is in the square. So if you add up 4 times 1/4, we get 1 white circle per unit cell. And then the atom B, the black circle, is located entirely within the square. And so the stoichiometry is AB. And if you look at that pattern, you would say, of course, there's equal numbers of A and B. So that makes sense. In the bottom exercise, our unit cell looks something like this. We have a rectangle as the unit cell. And once again, the rectangle is going to have a white circle at each corner of the unit cell, and then there's going to be a dark or black circle at the center of the unit cell. And so we would say that this is an example of a rectangular lattice. And then we might say, but is it a primitive rectangular lattice, or is it a centered rectangular lattice? And you might be tempted to say it's a centered rectangular lattice because there's an atom at the center of the unit cell. But that would be wrong, because the atom at the center of the unit cell is not the same as the atom that's at the corner. So if you were to be sitting on this lattice point right here in the center, you would say, I have 4 white circles that are neighbors and 2 dark circles that are neighbors. But if you were to sit at this lattice point, you would say the opposite. I have 4 dark circles that are neighbors and 2 white circles that are neighbors. All right, so those 2 points are not equivalent. And therefore, this is a primitive rectangular cell, not a centered rectangular cell. Once again, we have 1 of each atom within the unit cell, so the empirical formula is AB. And looking at the repeating pattern of atoms, I think you should see that you would have 1 white atom for every dark atom. Okay, so that's lattices in 2 dimensions. But a lattice by itself is not a crystal structure. To obtain a crystal structure, we need to put some atoms into the lattice. So we can think of the lattice points as the framework, or maybe the scaffolding from which we're going to build our crystal. But to build a crystal, we have to associate 1 or more atoms with each lattice point. Now, if we just put 1 atom on every lattice point, then, the crystal structure looks very much like the lattice, right? But we are not limited to just putting 1 atom on every lattice point. I mean, if that was the restriction, how could you have compounds? How could you have anything more than just 5 elemental solids? And of course, that's, as we know, far too limiting for what the world of solid-state chemistry is going to give us. So here, let's do an example. Here I'm going to take a group of atoms, which I call a motif, and I'm going to put that motif on each lattice point. And from that, I'm going to build up my crystal structure. Here my motif is a CuO2 unit, copper O2, and I'm going to choose to put the copper atom directly on the lattice point with the oxygens pointing down and to the right. Now, for it to be a crystal, it means every lattice point has to be identical. So I have to put that same motif associated with every single lattice point. And when I do that, Then I'm going to build this up, the extended structure. Of course, in a real crystal, this would go on thousands or millions of motifs or lattice points in each direction. But here I'm just going to stop with this number. Now, if I were to look at this and I were to, let's say, draw in bonds, are there bonds between neighboring motifs? The answer is yes. And so you see that I would have this kind of connectivity of my crystal structure. So each copper would be surrounded by 4 oxygens in a square planar environment, and each oxygen is surrounded by 2 coppers in a linear environment. Okay, and so this CuO2 layer, in fact, is a really important building block of the cuprate high Tc superconductors that you might get to in the next class with Dr. Wu. Okay, so that's how we build up a crystal structure from the combination of a lattice and a motif, or sometimes the motif is also called a basis. Now let's do another example. I'm going to let you do this example. Here we have a hexagonal 2D lattice, and we're going to have a 2-atom motif, and they're both going to be carbon atoms. And in this example, I'm going to place the 2 atoms from the motif here inside my parallelogram, not on a lattice point. So it's not required that an atom go on the lattice point. But if we associate these 2 atoms with this lattice point, it means that every other lattice point has to have 2 atoms displaced by exactly these vectors from it. What I would like you to do now is to complete this crystal structure and figure out what is the coordination number of the carbon atom. How many neighbors is it bonded to? And then if you can, you might see if it looks like a familiar crystal structure to you. So let's pause the video now, have you do that, and then we'll come back and discuss the answer. Welcome back. What did you get? Well, let's fill in the rest of our unit cells on this drawing by adding in this 2-atom motif associated with each and every lattice point. Of course, when we do that, this should start to look familiar to you. We can see here that each carbon atom makes bonds to 3 neighboring carbon atoms, which are pointed at the corners of an equilateral triangle away from the central carbon atom. And this is the structure of graphene. Or if you want to think about a bulk material, you could think about one of the layers that you might find in graphite. Okay, so in this way, we see how we can build up a crystal from a hexagonal lattice. We see that the motif, or the basis, doesn't have to go exactly on the lattice point. And we also learn from these 2 examples that the coordination environment we see in the motif is not necessarily, in fact, generally not going to be the same as what it really is in a 3-dimensional crystal. Now, at this point might be an interesting time to go back to when we were talking about tiling shapes and the triangle. Right, so we said, yeah, you could tile all the shapes with a triangle, but you couldn't do it without like rotating or reorienting the triangle, right? So if we were to draw a bunch of triangles here, and I've shaded them in orange so you can see them, you can see that does not tile all space. But it's also immediately apparent that if you were to use another set of triangles that were pointing down instead of up and stack them on top of it, think of them as what your eyes are probably seeing as the white triangles, that would tile all space. So what are we talking about there? What kind of lattice would that be? To answer that question, let's put a lattice point, if you will, or an atom, if you want to think about it that way, at the center of each triangle. There's for the triangles that are pointing up, and there's for the triangles that are pointing down. And when we do that, what do we have? Well, actually that might look kind of familiar to you. Can you see the 6-fold rings that we saw in graphene? Yeah, maybe it's a little easier if I get rid of the orange shading. And you should be able to see these edge-sharing 6-fold rings. You should be able to see that each lattice point has 3 neighbors that are pointed towards the corners of an equilateral triangle. Right? So this is just the graphene structure. And what that means is that the repeating unit, the unit cell, is that hexagonal 2D unit cell that we show in blue. Okay, so the kinds of structures you get from tiling triangles together are really not any different from the kinds of lattice that you would get from tiling hexagons together.